rather than doing everything the same, or you can look it as a way to reduce the number of error. I will show you what. So at point C, right, where you have x is equal to 0.8 plus 2.4 is equal to 3.2 meters. Okay, so we are going to analyze from right to left. Okay, so let me show you what I mean. Okay, so this is our geometric datum. So this is our point A. Okay, so we know that the distance, I'll draw the beam. So the beam I'm drawing now is point D, point C to point D. Okay, so this is our point C, and this is our point D. And we know at point D we have a load down here, and that load is, I can't remember now. Okay, sorry. The load is, I think, 40. Yep, 40 times 10 to the power 3. Okay, so we know this distance from here to here. Let me use a different color. So we know the distance from here to here, right? So this distance is 3.2 meters. Then the distance from here to here is 4 minus 3.2. So this is equal to 0.8 meters, right? So I'm going to do my analysis from right to left. Okay. So when you do so, this is analysis from right to left. All right. So right to left means this is the analysis direction. Right. Before that, we have been doing left to right. Now we go from right to left. So when that's the case, right, this will be your V at point C, and then the moment at point C. Okay, the moment at point C. So why I do that is because I only need to consider this load over here. I no need to consider the load at point B and the evenly distributed load. Okay, it makes your working much quicker. Okay, so where I want to show you is, yeah, all this analysis is from left to right, right? You can see the direction. You can see the direction of your shear force and bending moment. Shear force or bending moment. So all these are left to right. Okay, see, left to right analysis. Then when we go from right to left, right, I want you to observe this. You have to flip it over. Okay, so now let's write down the shear force and bending moment constant. Okay, so positive is going up. Summation of forces in the y direction is equal to 0. So you have 40 times 10 to the power 3. Okay, and then plus by V at point C is equal to 0. So V at point C is equal to minus 40 times 10 to the power 3 Newton. Okay, so you can also use, okay, you can also use this equation down here. Okay, you can also use this equation down here to check, right? So at point C, okay, so let's check at point C, right? Z is equal to what? 3.2 meters. So if you use this equation over here, it should be the same. Okay, so V at point C is equal to minus 50 times 10 to the power 3 multiplied by 3.2 plus by 120 times 10 to the power 3. Okay, so this is equal to minus 50 power 3 times by 3.2 plus by 120 power 3. So this is also equal to minus 40 times 10 to the power 3 Newton. See, it's the same. Okay, then you take moment now. Okay, so we take summation of moment in the x along the x or on x-axis as a distance of 3.2. It is equal to 0. Okay, so you are taking moment down here now. Okay, you're taking the moment down here. So it's equal to 40 times 10 to the power 3 multiplied by 0.8 is positive. So 40 times 10 to the power 3 multiplied with 0.8. And then you it's going in the clockwise direction, minus moment about point C is equal to 0. So moment about point C is equal to 40 power 3 times 0.8 minus 32. Okay, minus 32 times 10 to the power 3. I'll write this out better. Minus 32 times 10 to the power 3 Newton meter. Okay. Or again, you can use this equation over here to check at point C where Z is equal to 3.2. So moment at point C is equal to minus 25 times 10 to the power 3 multiplied by 3.2 squared plus by 120 times 10 to the power 3 multiplied by 3.2 and minus 96 times 10 to the power 3. So this will be equal to so minus 25 power 3 times by 3.2 squared plus by 120 power 3 times by 3.2 minus by 96 power 3 is equal to 32. Minus 25 power 3 times by 3.2 squared plus by 120 power 3 times by 3.2 minus by 96 power 3. So it's also equal to, sorry, this is positive. I do apologize. Okay, it's not negative. So if you use the equation above, it's also the same thing. Okay. Right, but we only, so over here, if you see this equation over here, you have to consider so many forces. Yes or no? You have a distributed load, you have a point load, right? Over here, you just only consider the point load. Okay, so less possibility of making mistakes. Okay, so you have 32 and 40. So you have minus 40 over here. And then you have 32. Okay. Then the next one, C to D. Again, I'm going to focus on the analysis from right to left. Okay. So I'll show you how this can be formed. Okay. So I'm going to save space. Okay. I'm going to save space. I'm going to write down here. Okay. So now, so you can copy the diagram. Okay. So now we are going to do from point C to point D. So now it's equal to 3.2 Z 4.0 meters. Okay. So again, we're going to do our analysis from right to left. So this is the geometric datum, right? So now the distance from here to here, right? This is our Z. Distance from here to here is 4 minus Z, right? So this is our structure. Okay. And then this is our point D. Our point D, we have a load down here. That load is equal to, is it 40 or 20? I can't remember now. 40. Okay, 40 times 10 to the power 3. Right, and then positive shear. Positive bending moment. So you only just have one force to consider, you know. So from here, positive in the y direction is equal to 0. So you have 40 times 10 to the power 3, right? Then plus by v as a function of z is equal to 0. So v as a function of z is equal to 40 times 10 to the power, so minus 40 times 10 to the power 3. Okay, so this is 40 minus 40 times 10 to the power 3. And then when we take our moment, right, when we take our moment, we have summation about forces, summation about moment, about the x-axis at a slider point at z distance. So this is where we again take our moment. So this will be equal to it's going in a clockwise direction, so 40, sorry, this is equal to 0 first. So it's 40 times 10 to the power 3, 4 minus z, and minus m, because going clockwise, as a function of z. Okay, so m as a function of z is equal to 40 times 10 to the power 3 multiplied by 4 minus z. Okay, so it is a linear function, minus 40 times 10 to the power 3 z, okay, and then plus by 160 times 10 to the power 3. Okay, so that is our function. Okay, so this is our moment is minus 40 times 10 to the power 3. Z minus plus by 160 times 10 to the power 3. Okay, and then the last one at point D, where Z is equal to 0, you know that the shear force at Z is equal to 0, and the moment about Z, there's no perpendicular distance, is equal to 0. Okay, so these are equal to 0. Right, so I know I took quite a while, but I want you to get used to it. Okay, why? As I said, in the next 2 weeks, we're going to look at deflection. You have to form the equations. Okay, so from here, we are going to sketch. I'm going to copy this whole thing across. Okay, we are going to sketch the shear force and bending moment equation, or bending moment diagram. Okay, we're going to sketch. Okay, so this is our, I make it smaller, so don't need so big. So now we're going to sketch, right? So we're going to sketch our shear force equation. So minus 40 and 80, that seems to be the range. Okay, so we're going to draw. So 0.8, 80. So shear force. So this is 80, 60, 40, 20, 0, minus 20, and then minus 40. We don't need to go beyond that. Then we have our x distance. So this is 0.8, 1.6, 2.4, 3.2, oh no, 2.4, yeah, 3.2, and then 4.0. No, I don't need so long.